Welcome to the Spring 2021 Chemistry 1412 Final Exam Review. So, a little bit of detail on how this final exam review is going to work. We are going to basically have this practice final exam available to answer and ask questions from. However, it's not going to be limited to this practice final exam. In fact, the first thing that we want to do is open it up to questions from you. They can either be from this exam or from your own homework problems or your own practice exams or anything that you particularly want to ask. So this is going to be a student-driven, student-focused final exam review. But if you're not sure exactly where to start, or if you don't really know, have anything ready or whatever, we can just go ahead and start with the practice final exam that we have here. So are there any questions that you would like to begin with, either from this test or from your own resources? Or is there any topic, generally speaking, you'd like to begin with?
Same here, I agree.
Okay, so maybe just go ahead and start with the first question and kind of work our way down the line.
Yes.
And if we see something repetitive, we can always skip it. All right. If we come to a question that you're like, I really actually already understand this, let's go ahead and skip it. Just let me know, we'll skip it. Okay. So first things first. A solution was prepared by dissolving 23.7 grams of calcium chloride in 375 grams of water. The density of the solution is found to be 1.05 grams per milliliter. What is the molar concentration of CaCl2 in this solution? Okay, so the first thing that we want to do here is recognize what on earth is molality. What on earth is molality? So let's go ahead and we'll insert an equation here. Molality, you should know, is essentially the moles of solute, divided by what?
I believe it was kilograms of solvent.
Kilograms of solvent. So moles of solute divided by kilograms of solvent. It's different from molarity. If we wanted to compare molarity would be moles of solute per liter of solution. So in this case, to solve for the molality, I have to solve for the moles of the solute, and then I have to solve for the kilograms of solvent. So I'll start with the moles of solute. So for this particular part, I'm going to go ahead and start with my grams because I can convert the grams of CaCl2 to moles, right? All I'm going to need to do that is what?
Oh, sorry.
What were you going to say?
I must apologize if I'm like already like answering too many of the questions.
No, don't feel bad. I mean, that's great.
Yes, sir. I was going to say you would multiply that with the molar mass for calcium chloride to get moles of calcium chloride.
Well, it said, so you'd have to divide with the molar mass, right?
Oh yes, sorry.
Yeah, no problem.
I was thinking of like multiply it with moles on top and grams on bottom.
Yeah, exactly. So you have CaCl2, whoops. And so this is on the bottom. If I calculate the molar mass, calcium is about 40.08 and chlorine is about 35.45. So if I add those two together, that's going to give me roughly about 110 point something or other, I don't know. 110 point, I want to say, 0.98. Yeah. Just did that in my head real quick, so it might not be totally accurate, but calcium is 40.08. 2 chlorine, so it's going to be 70.90. That should add up to about 110.98. Okay, so this is going to give you 1 mole of calcium chloride. So I'll just go ahead and calculate that, and what do I get? So you guys are going to be my calculators. I'm going to trust in you to give me the right answers. Yeah, so that's going to be 0.214. Very good. So 0.214 moles of calcium chloride. Now note something interesting here. They start with only 3 sig figs, so you only have 3 sig figs in your answer. So that's good. Okay, so now we have the moles of calcium chloride. We also need to get the kilograms of solvent. So the kilograms of solvent, I'm going to start with my grams of solvent, which are already given. So I'm going to, once again, insert a little equation, 375 grams. And then I'm going to go ahead and convert the grams to kilograms. Unfortunately, this is a pretty simple conversion. In fact, you may not even need to type this out. You may be already able to do this in your head. And if you can, that's fine. But just because I find altogether too often when my students do things in their head, there's oftentimes mistakes. Even the smart ones make mistakes. So sometimes it's good to write it out. But 0.375 kilograms. All right, so I now have moles of solute and kilograms of solvent. So now all I have to do is divide those two by one another. So I'll take the moles of calcium chloride here, and I'll take the kilograms of solvent here. Water's the solvent. And then I will simply go ahead and divide one by the other. And if I do that, what do I get? Yeah, 0.569 molar. Or molal, rather. So this would be the answer to this question. Now, you might ask yourself, well, why does it have density in there? It gave us the density and we didn't use it for this equation, or we didn't use it for this problem. The truth is that sometimes professors give you more information than you actually need. Sometimes you'll be given information that's not necessary to solve the problem. So focus on what the problem is asking for, and don't necessarily try to figure out a way to use every single piece of information in the problem, because there may be problems like this one here where you actually don't have to use everything that the problem gives you. Any questions on that, or does that make sense? All right, cool. All right, so now let's go to the next one. It says calculate the molality in a solution prepared by dissolving 16 grams of urea and 39 grams of water. That's very similar to the one we just did. Should we just go ahead and skip that one? Just another moles over kilograms. All right. So then let's go ahead to number 3. It says a solution containing 100 grams of an unknown liquid and 900 grams of water has a freezing point of negative 3.33 degrees Celsius. Given the 1.86 degrees Celsius per molal for water, the molecular weight of the unknown is what? So I'm solving for the molar mass here. Now this is a really interesting problem, and it's an interesting problem for a couple of reasons. You're asked to solve for something that it is not, you're not going to be able to solve for it directly, but also it's not something that we usually think of as chemical formula. So first of all, we have to understand, how would you calculate molecular weight if you couldn't look at something in the periodic table? If you couldn't look at the periodic table to calculate the molecular weight, how would you solve for the molecular weight? Sometimes known as the molar mass. The molar mass would be what? Now it further makes it a little bit tricky because it says AMU as the unit, but Yeah, grams per mole, grams divided by moles. The unit of molar mass is usually grams per mole. And we know that so it's going to be the grams divided by moles. And even though it says the molecular weight is AMU, the only difference between the molar mass and the molecular weight is that the numbers are going to be the same, but the units are going to be different, AMU versus grams per mole. Now, obviously, it's a little bit more complicated than that. However, even though it's a little bit more complicated than that, this will work for our purposes. Now, in this case, what does it give you regarding this unknown liquid? Does it give you the grams of unknown liquid or the moles of the unknown liquid? What does it give you initially? It does actually give you the grams, yeah. So I'm going to put this 100 grams of unknown because it tells me 100 grams of unknown. Now I need to solve for the moles of the unknown. This is what I don't know. So there's no way to solve for the moles of this directly. However, I do see I'm given another useful piece of information here in that it shows me that the freezing point is negative 3.33. It also happens to make note of the fact that the freezing point depression constant is this. From this, you should surmise that the freezing point depression equation is likely going to be needed here. So, what is the freezing point depression equation? Basically, that is going to be that the change in the freezing point, otherwise known as delta T, and I wanted to be really precise, delta TF is equal to negative K, and specifically KF, freezing point depression constant, KFM, where M is the molality of particles. However, you may also see it in terms of IKFM, in which case the molality will be the molality of the solute. Now, as a general rule, I kind of like the IKFM a little bit better just because it reminds me that I have to look for if the compound breaks up into ions. In this case, it's an unknown liquid. Typically, ionic compounds are not liquids. So we can assume that this is probably molecular. Plus, we're not given the formula. So we can when we're not given the formula of something, we kind of have to go ahead and just assume that, okay, well, this is not going to actually be ionic. Furthermore, it tells you that this is the molecular weight of the compound. And obviously, ionic compounds don't have molecules. So in a formula, in this case, then, the number of ions it breaks, the number of particles it breaks up into, that's what the I is, the Van Hoff factor. The number of particles this breaks up into is 1. It doesn't really break up, so it'll just be 1. So I can actually just eliminate that and simplify this to delta TF is equal to negative KFM. All right, that's great. Now, let's see what we have here. We're looking at this particular formula. What are the pieces of information that we are given in this problem that we can substitute in? The change in temperature and the KF value, exactly. So the change in temperature is this negative 3.33 because it says water has a freezing point of negative 3.33. So this problem actually does expect you to know what is the normal freezing point of water. 0 degrees Celsius, yeah. So T final minus T initial is the change in the freezing point. Well, T final is given here. The final temperature is negative 3.33 degrees Celsius. T initial, the ordinary freezing point of water, is 0 degrees Celsius. So, and then I'm also given the KF here, and the KF happens to be the 1.86 degrees Celsius per molal. Oh, come on. I do not love you right now. Like the Shaw. Womp. Ah. Ah. I love that even less. My apologies. I'm having issues. Let's do that. I want to do it this way. 3 Celsius per mol. There we go. So notice that I do actually have to look at what the change in the freezing point is. It's not simply the freezing point, it's the change in the freezing point. And the change in the freezing point is always the solution minus the solvent. The solution minus the solvent. Or you can kind of think of it as final minus initial. Final in terms of after you add the solute, and initial would be like before the solute. But yeah, solution minus solvent is going to give you the change in the freezing point. And the change in the freezing point when you add a solute should always be negative. It's always going to reduce the freezing point. And this is why we have this negative KFM. Not positive KFM, but negative KFM. Now, I will say this, your book and your lab book, depending on which book you use, some books say positive KFM, some books say negative KFM. Some books just look at the absolute value of the change in the freezing point, and they look at and so because they look at just the absolute value in the change in the freezing point, they just leave this as a positive all the time. But it is more precise to call this negative KFM because freezing point depression, by the very name, if you add a solute, does it cause the freezing point to go up or down? If you add a solute, does it cause the freezing point to go up or down? Yeah, it goes down. And because it goes down, the change in the freezing point should always be negative. Okay, so I crunch my simple numbers here. I don't actually have to crunch very hard. This isn't a very serious intellectual workout, at least not this part. And then, so basically negative 3.33 minus 0, just negative 3.33. If I divide both sides by negative 1.86, so I can solve, because I'm solving for this guy, right? I'm solving for the molality, at least initially. So then I'm going to simply go ahead and take this, and I'm going to divide by all of this. There we go. And so molality is going to be equal to, let's pull this over to the other side. There we go. Molality is going to be equal to negative 3.33 divided by the other, by negative 1.86. And what does that give you for molality? I calculate. What does that give us for molality? Yeah, 1.79. So this is going to be 1.79 molality. Okay. Well, remember, we got to keep our focus on what we're trying to solve. What we're trying to solve for is the molar mass. And to solve for the molar mass, I need the moles of the unknown. I still don't have the moles of the unknown. I have the molality. However, if we go back up to our little formula up here, the molality is equal to the moles of solute over the kilograms of solvent. So I can actually solve for the moles of the unknown now because I have the molality and I have enough information to solve for the kilograms of solvent. So the molality, of course, is just going to be the 1.79. Kilograms of solvent, though, I see that I have 900 grams of water. Well, 900 grams of water is not kilograms, but since all you have to do to get kilograms is divide by 1,000, this is going to be 0.900 kilograms of solvent. Now, if I want to solve for the moles of solute here, I'm going to have to multiply both sides by the 0.9 kilograms. To get rid of a denominator, I have to multiply both sides by the denominator. I'm going to go ahead and do that here. Multiply both sides. Come now. Let's behave. Behave, Microsoft. Behave. All right. Bam. And bam. Multiply both sides. That means my kilograms of solvent is going to cancel out. Actually, the 0.9 will cancel out as well. And then I'm going to get molality times kilograms of solvent is equal to moles of solvent, or solute rather. And that's going to give me what? And I think somebody answered my question for me. Yeah, 1.611. So 1.611, and it's really only going to be 3 sig figs, so 1.61 moles of solute. So this is my moles of solute. Just as a side note, in case you like to use conversion factors like I do, you can also, if you had preferred, you could use the molality as a conversion factor because molality means moles of solute per kilograms of solvent. So if I wanted to use it as a conversion factor, I could start with my grams of solvent, which is 900 grams, and then I could go ahead and convert that to kilograms by 1,000 grams is 1 kilogram. And then I can go ahead and use my molality, and I can convert my kilograms to moles because molality means moles per kilogram of solvent, and 1.79 molality, 1.79 moles of solute for 1 kilogram of solvent. And if you did that calculation, you'd end up with the exact same thing, which is 1.61 moles of solute. So if you like the conversion factor way, you can definitely do it. If you want to just use the molality formula, you can use that as well, or like the molality formula down here rather. Whatever works best for you, whatever makes it easier for you, go ahead and use that. So I now have 1.61 moles of solute. I can pop that up here. Now I have the grams of the unknown and the moles of the unknown. This is my unknown solute. And then I can calculate that. Oops. Try that again. And what do I get for my molar mass? So yeah, it should be a 100 divided by 1.61. And that should get, well, oh wait, 100 divided by 1.61. That should give you about 62.1. So there we go, 62.1 grams per mole. Or AMU, if you're talking about molecular weight. Did that make sense? I realized that that was a complicated problem. That'll also likely be a problem that you'll get on your lab final exam when that comes up. I don't know if you've already had that though. All right. Now, if you have any problems that come to mind that you're like, you know what, I would like to go over this particular type of problem or whatever, just let me know and we can just jump straight to that. Totally fine. So number 4 is more of a conceptual problem. It's wanting you to recognize the effect of ions on freezing point depression. So it said a 0.1 molar, or 0.1 molar aqueous solution of each one of these solutions would have which one would have the lowest freezing point. We have to recognize that they're all 0.1 molar aqueous solutions of the compound, but freezing point, lowest freezing point, if we look at the equation for freezing point depression, delta TF is equal to negative IKFM. The greatest or the most negative change will be the one that has the highest or lowest molality. Well, it would be the highest molality, right? I'm looking for the most negative value of this. However, in this case, the molality is the same, or the molarity and molality is going to be the same because it's all a 0.1 molar aqueous solution. So for something like this, what I want to do is I want to actually look for the biggest change, the biggest differentiating factor, and that is I. Okay? Because the molarity and the molality, if the molarity is the same, the molality is going to be close to the same, especially in a dilute solution like this. So basically, whichever one of these breaks up into the most ions is going to have the high or the most negative change in freezing point. So which one of these substances will break up into the most ions? Yeah. So yeah, for this one is only going to break up into 2 ions, Na and Cl. Aluminum nitrate, that's going to break up into 4 ions. Potassium chromate, here's where you got to be careful because you have to recognize chromate, CrO4, as a polyatomic ion. So that's just 1 ion plus the 2 potassiums. So that'll break up into 3. Likewise, sodium sulfate. Sulfate is a polyatomic ion, so that's only going to break up into 3 ions as well, 2 sodiums and 1 sulfate. That's going to be 3. So this does definitely require you to know your polyatomic ions. And of course, sucrose is molecular, so it would just be 1. And clearly then, if that's the case, this is going to be your lowest freezing point, or the most negative freezing point. Do you want to bother with 5, or should we just go ahead and skip that? Okay. Yeah, it's just a, it's just a, it's just a freezing point depression problem, and it's just glucose, so that the I would be 1. So yeah, it's a pretty straightforward plug and chug type question. Okay, so let's go ahead and skip to number 6 then. If we skip to number 6, this is a rate problem. It says, consider the following reaction. At 300 degrees Celsius, the concentration of NO2 drops from 1 or 0.01 molar to 0.00650 molar in 100 seconds. The rate of appearance of O2 for this is what? Okay, so this problem really requires you to know a few definitions. And this is one of the trickiest things about the rate stuff. Most times, students tend to have a little bit of a lack of precision with their language, and it causes them to get confused with these types of problems. So first of all, one of the things that I would do with this particular problem is write up the rate expression for this reaction in terms of each of the reactants and products, okay? Because this is also the type of question you could get potentially. So the rate of reaction here, notice that this is the rate of reaction, not the rate of appearance, not the rate of disappearance, the rate of reaction. The rate of reaction here is basically just going to be, in terms of the first substance, NO2, the change in NO2 concentration over the change in time. But since I have to put this all in the same frame of reference, because this has a coefficient of 2 here, I'm going to put a 1/2. I'm going to have it so that it's on par with the other ones. So I'll use the fraction of the coefficient. Another thing is, because this is a reactant, is the amount of reactant in the course of a reaction going to go down or go up? Yeah, the amount of reaction is decreasing. So the change, and change, remember, is always final minus initial. Change is always final minus initial. The final amount is going to be less than the initial amount. That's going to make it negative, right? So, and just to kind of emphasize that point, delta NO2 is always, change in concentration is always the final concentration minus the initial concentration. All right. And so this is going to be negative because the final amount is always going to be less than the initial, because as the reaction proceeds, reactants get used up. Well, here's the thing. You can't actually have a negative rate of reaction. You cannot have a negative rate of reaction, because that would mean the reaction is going backward. Okay? So whenever you express rate of reaction, it must always be expressed in terms of positive value, positive number. Since the change in NO2 is always going to be negative because it's a reactant, I end up having to put a little negative sign in front here. I'm going to put a little negative sign in front here to change that negative value into a positive. The negative of a negative is a positive. Or as one of my students used to tell me, it's kind of terrible, but she used to say, if bad things happen to bad people, that's good. A negative times a negative is positive, right? I guess that's terrible, but yeah. Um, no, we should never wish bad things to happen on anybody, but yeah, no, it was kind of funny. It actually made me laugh. All right, so in this case then, that would be the rate of reaction with respect to NO2. Now, with respect to NO and O2, those are both products. So the final minus the initial will always end up being a positive value for them. So for them, I won't have to put that negative sign in. However, I will have to use that fraction of a coefficient. So it's going to be delta N, that change in the concentration of NO over delta T. And if that's the case, I'm also going to do 1/2. So, because once again, the coefficient is 2, I use the fraction of the coefficient so that they're all in the same, so that the rates are all expressed in the same, as the same amount. All right, next, oxygen. So it's the change in oxygen, O2, over the change in time. Once again, because it's a product, there's going to be more at the end than there is at the beginning. So it's going to be a positive number. I don't need to put that negative sign. I only put the negative sign for the reactants. And in this case, the fraction of the coefficient, well, it's just 1/1. Well, 1/1 is just 1. So that's kind of stupid. I don't actually even need to put those. So those are 3 expressions for the rate of reaction. 3 expressions for the rate of reaction for this substance. Now, one of the things that you would want to note here is that if we're looking at individual pieces, I can classify this part here, this negative delta NO2 over delta T, this actually gets a special name. This is the rate, and because it's a reactant, this would be called the rate of disappearance. Rate of disappearance. So this is the rate of disappearance. And then if I look at just this part, now this does not, of course, this doesn't include the 1/2. This, because it's a product, this would be a rate of appearance. So this is the rate of appearance. Specifically, that would be the rate of appearance of NO. In this case, what the problem is actually asking you for is the rate of appearance of O2. Well, the rate of appearance of O2 is this. The rate of appearance of O2 is this. So this is what you're actually being asked for. You're actually asked for this. Now, even though this equation looks like it's complex and such, solving this problem is actually really not that hard. All you have to do is recognize I'm given information for NO2, the final and the initial time, and also the time, or the final and the initial concentrations and also the time. And note that with that information, I can take this, because remember, all these expressions are equal. I can take that and I can set it equal to the other one. So, go ahead. Ah. Yeah, why not? There we go. I want to see if I can, there we go, that'll work. Insert equation. So I'm going to go ahead then and solve for the rate of appearance of O2, which is basically, like I said, it's just a, cool. So, where's the delta when I need it? Come on. Alpha, beta, gamma, delta. Here we go. Delta NO2 over delta T. And actually, I have to include a -1 divided by 2, -1/2. -1 over 2. Well, that negative on the inside. Okay. That's going to be equal to that delta O2 over delta T. That's a sign of my laziness that I feel the need to copy and paste that. That really didn't save me much time at all. Technology makes me lazy. Okay. So all I have to do here then, actually I'm going to go ahead and switch sides here. All I have to do here is plug in the values. All I have to do here is plug in the values. So I'll take the change in NO2 is just going to be the final minus the initial, and the final is going to be that 0.00650 molar minus the initial, which is the 0.100 molar. Oh, 0.010 molar. I lied. And then the change in time is just going to be the 100 seconds. And then all I have to do is plug that into the calculator, and if I do, what do I get? That's right, 1.75 times 10 to the -5. 1.75 times 10 to the negative fifth, or if I wanted to do it in scientific notes, I mean, if regular notation, do 0.0000175. I already started in scientific notation, so I'll just do that. Bam. All done. Easy as pie. Which, whoever came up with that phrase probably never actually made a pie. It's a little tricky to work with. Okay. 1.75 times 10 to the negative fifth. So, now, so this is another example of a problem you could get. So consider the following reaction. Give an expression for the average rate of appearance of B in terms of the average rate of disappearance of A. The average rate of disappearance. So, and in this particular case, we were to do the same thing. Actually, I think I'm going to draw because I think that'll be easier. So once again, do a rate expression for each one, and negative 1/3. You can put the negative on the inside or the outside. Sometimes I like to put it on the outside. Negative 1/3 delta A over delta T is equal to positive 1/2 delta B over delta T. Now it wants an expression for the average rate of appearance of B. In other words, it's wanting you to solve for this in terms of the average rate of disappearance of A. So basically, just rearrange this equation and solve for that, what I've circled in green, delta B over delta T. That basically means I just multiply both sides by 2. So even though it looks kind of complicated initially, if you recognize how to put together one of these rate expressions for each of the substances, this is actually a really easy question. All you have to do is multiply both sides by 2, and you'll get that the delta B over delta T, which is your rate of appearance of B, is equal to negative 2/3. I multiply both sides by 2 to cancel out the half. Negative 2/3 delta A over T. So that gives you this answer. Now, strictly speaking, there is a little bit of imprecision in the way that they're using the term. Technically, the average rate of appearance of A would actually be a negative delta A over delta T, but it is what it is. And there's only one answer that actually gives you the proper fraction, which is the negative 2/3 or the 2/3. So there you go. Any questions on that rate stuff? That rate expression stuff? Does that make sense? No, because see, here's the thing. You're actually trying to solve for the rate of reaction with respect to, or you're trying to solve for the delta B over delta T. The given expression for the average, notice what it's looking for. Given expression for the average rate of appearance of B. Give an expression for the average rate of appearance of B, which means I want to solve for delta B over delta T. Yeah, it's tricky. Yeah, with some of these problems, you really got to watch the wording. It's very easy to be led astray, shall we say. Yeah, no problem. It's a good question. Very good question. So let's go ahead and take a look at the next one. It says, which of the following does not play a part in determining the rate of reaction? So this kind of comes down to the kinetic molecular theory of reactions. And basically the kinetic molecular theory states that reactions occur when molecules or atoms collide with enough energy, so they're moving fast enough, and at the precise orientation, the correct orientation that they need to collide in order for the reaction to work. So they collide at the precise place that they need to collide, and they collide with sufficient energy. So which one of these would not play a part in that? So temperature. Is temperature going to play a rate in either the molecules having energy or the molecules colliding in the right spot? What do you think? Yeah, it definitely does play a part. Temperature is going to increase the speed of the molecules, so they're going to collide with more energy. Plus, because the molecules are moving more quickly, or rather, because there's more molecules moving more quickly, they're going to collide many more times than they would if they were moving more slowly. It's like if you have a bunch of little kids in a play area. If there's more kids, they're going to collide more more often. Or if they're running around, they're going to collide more often, usually with disastrous results. But yeah, so effectively, the energy distribution curve kind of looks like this. So at lower temperatures, you have much more molecules with low energy, and then you do kind of have a little bit of molecules at a higher energy. At higher temperatures, it's a more extended distribution. So you still have molecules at low energy, but you also have a lot more molecules at high energy. And if, like, say, for example, the molecules need, say, this much energy to react, notice there's a lot more molecules, a lot more shaded area. There's a lot more molecules. This is, of course, the number of molecules. Or actually, yeah, and this is the energy. There's a lot more molecules that have the higher energy at a higher temperature. Okay, so temperature definitely makes its presence known. What about the concentration of reactants? Once again, you can think of our little kids example. If there's lots of little kids in an area, they're going to collide more often, right? Just because of the fact there's more kids in the area. If there's a few little kids, they're not going to collide as often. There's lots of little kids, they're going to collide more often. And therefore, like same thing with reactants, they're going to collide more often, therefore there's going to be a higher percentage of those, the same percentage rather is going to be successful. The same percentage is going to be successful, but there's going to be a larger number of collisions that happen, and so therefore there will be more successful collisions. So concentration, definitely higher concentration increases the rate of reaction. What about the presence of a catalyst? Yeah, the presence of a catalyst is going to affect, because it actually creates a different mechanistic pathway with a lower activation energy. So a catalyst is going to effectively take this line and it's going to move it over this way. It's going to basically reduce the amount of energy needed to make the reaction go. It does this by opening up a new reaction pathway. So that definitely increases the number of molecules that can react, and it'll increase the rate of reaction. What about surface area, solid or liquid reactants? Yes. That's right. Bigger kids have a greater chance of colliding. Although, no, interestingly enough, in the case of surface area, if the particles are broken up into smaller pieces, it actually gives them more surface area. So smaller pieces means more surface area because the same amount is broken up and more is exposed. This is why powdered metals, I don't know if you've ever had any experience with powdered metals, but powdered aluminum, powdered copper, these things are extremely flammable. In fact, explosively so. Powdered aluminum is actually, or powdered iron or powdered aluminum, maybe both, is actually what thermite is made of. It actually burns really hot. So powdered metals, or like increasing the surface area of something, increases the available atoms or molecules for reaction. Because it's only and if you have a crystal, if you have a block of a particular substance that's a solid, only the exposed area, only the outer surface is going to be able to react. The inner surface is protected. So, yes. But I do like the analogy. I thought that was great. So that leaves us with the equilibrium constant. And although it's not entirely obvious, because the others are definitely things that do affect, the answer is actually going to be E. Yeah, the equilibrium constant actually has no effect on the rate of reaction. The reaction rate will be the same regardless of what the equilibrium constant is. The equilibrium constant just determines when the where the reaction stops, or where the reaction reaches equilibrium. It'll react until it reaches the appropriate equilibrium point, at which point the forward reaction and the reverse reaction will be equal, and you will not get a change in the substances. But equilibrium constant itself doesn't determine how fast it reacts, nor does the rate of reaction determine what the equilibrium constant is going to be necessarily. Cool. Well, that was fun. Let's take a look at number 9. Now, number 9 is a pretty standard problem, and so I think this is a really important one for us to go over. A lot of it also because I don't like the way in which a lot of times this particular type of problem is explained, just because it's usually not explained in enough detail, and students are left wondering what the heck is going on. So I need to determine the overall order of reaction. So we've already dealt with the rate of reaction in terms of change over time. This is actually a measure of the average rate of reaction. Otherwise, this is sometimes these types of rate expressions, these are sometimes called differential rate laws, or differential. Actually, I should have it point to this. This would be like the differential rate law, having reference to calculus here. So differential rate law as opposed to the integrated rate law. We'll talk about the integrated rate law shortly. But as opposed to those rate laws, there's what we more standardly think of when we have rate laws. And basically, a standard rate law for a reaction is going to be like, let's say if we have reactants A and B, as in this case, the rate law for the reaction is equal to some rate constant K, which I don't know, it's usually lowercase k, it's a lowercase k, times the concentration of A to the m power times B to the n power. Now m and n are the powers of, or the order of reaction with respect to each of those reactants. Now you could use X and Y, like little a, little b, M, N. It doesn't really matter what you use for those powers, but typically we just use M and N. And O if there's a third one, a C. So in this particular case, what I'm going to go ahead and do is I'm going to set up rate expressions for 2 of the experimental trials. And I'm going to do this in order to figure out what the order of reaction is with respect to a particular variable. So for example, if I wanted to figure out what the order of reaction is with respect to A, I want B to remain constant. Well, if I look at these, B remains constant, or the B is the same for experiments 1 and 3. Since B is not changing, I can use this to figure out what the effect of A is on the rate. Generally speaking, I like to put the one that has the higher rate on top, just because that's going to actually make it a little bit easier when I do the calculations later on. Okay, so experiment 3 is going to go on top. I'm going to write 2 rate expressions. So the rate is actually given as 25.47 molarity per second. And that's equal to K times the concentration of A, which is 0.819, to the M, times the concentration of B, which is 0.763, to the N. And then I'm going to set up a rate expression for experiment 1. Now for experiment 1, the rate is 2.83 molarity per second. Is equal to K, rate constant, times the concentration of A for experiment 1, which is 0.273, times the concentration of B, which is 0.763. Once I've written these 2 expressions, I can actually divide them. I'll go ahead and divide them. And the cool thing about dividing these expressions is because M and N are going to be the same for both of them. Those are the orders of reaction. And the constant is going to be the same, otherwise it's not a constant. So the constant cancels out, and 0.763 to the N cancels out. I don't know what N is, but it's going to be the same for both of those, and 0.763 is the same, so they're going to cancel out. This allows me to get rid of 3 variables, well, 2 variables, and so I only have 1 variable left, which is M. I can now actually solve for M. So 25.47 divided by 2.83 is roughly 9, and 0.819 divided by 273 is approximately 3. So I get 3 to the M is equal to 9. In that case, what is M? 2, yeah. 3 squared is going to be 9. So M is the second, oh, that's not what it is. M is going to be the second power, 2. So this is second order with respect to A. I know that this M is actually a 2 now. I can then do the same thing for B, but you'll notice here, well, I'll go ahead and do it anyway. I can then do the same thing for B. I need to keep A the same, so I'm going to use 1 and 2. In this case, the rates are the same. I'll just use the higher concentration of the substance that I'm looking at, B. So I'll put experiment 2 on top. So here's experiment 2. And once again, I'm going to write out a rate law. it's 2.83. Molarity is equal to K, little k, times the concentration of A, which is 0.273, to the second power, times the concentration of A, or B rather, which is actually for experiment 2, it's 1.526. And this is molar 2. Okay. And this is to the n power, because I don't know that one. Experiment 1, I'm going to take the data from experiment 1. It turns out, if I look at experiment 1, it's also 2.73 molarity per second. And that's equal to K times 0.273 molarity squared times the concentration of B, which for trial 2 is, or for trial 1 rather, is 0.763. So this is going to be 0.763 molarity to the n power. Well, 0.273 squared over 0.273 squared, when I divide these, that's going to cancel out. So 0.273 squared, 0.273 squared, that's going to cancel out. And then I'm going to go ahead and cancel out the K as well, because I don't know that one. And then at this point, all I have to do is divide the two sides. I've canceled out two, or well, in this case, one variable. And this gives me, on the right-hand side, this is about 2 to the n. But on the left side, because it's the same thing, it's just going to be 1. Anything divided by itself is 1. So 2 to the n is equal to 1. Well, the only way you can raise something to a power and have it be equal to 1 is if the power is what? Yeah, 0. So n is actually equal to 0. So this is actually a 0 order reaction with respect to B. So this n up here is actually a 0. Okay. So if I were to rewrite the rate law for this reaction, I would say that this rate is equal to equilibrium constant K times A squared. And I wouldn't have to put B because B to the 0 is just 1. Since this 0 power means it has no effect on the rate. This is your rate law. As far as the overall order of reaction, to get the overall order, I just add the individual orders. So the order with respect to A is 2, the order with respect to B is 0, and 2 plus 0 is 2. So the overall order of reaction with this particular experiment is going to be 2. Does that make sense? Now, if you are particularly sharp and you don't need to write out all this to solve for the order of reaction, that's fine. Some people can just look at the ratio of the rates. So some people can just look at, okay, I see that if I compare these two, for example, B is changing, but the rate's not. Oh, that must be a 0 order reaction. And they say, okay, well, if I compare 3 and 1, B doesn't change, but A changes. If I divide if I divide these two by each other, that gives me 3. These two by each other gives me 9. Oh, okay, well, it's going to be 3 squared. So the order is going to be 2 for the A. Now, if you can do that in your head, that's great. But it is useful to recognize that this is what it comes from, because it will help you to do it in your head faster. And furthermore, if you don't remember how to do it in your head, you can always do it this way. So So now let's look at number 10. For number 10, I may have to zoom out just a bit. All right, so it says, which one of the following, go away. Which one of the following graphs shows the correct relationship between concentration and time for a reaction that is second order in A? So this requires you to be familiar with your integrated rate laws. Is your professor planning on giving you a list of the different equations? Do you know offhand, or do you have to have them memorized? Okay. So based on the list of equations you have, if you have the list of the integrated rate laws, which integrated rate law corresponds to a second order reaction? It's actually not. Actually not A. So a zero order uh, uh, no, actually A is first. So a zero order reaction has an integrated rate law of concentration of A at time t is equal to negative kT plus A initial. First order reaction has an integrated rate law. First order reaction has an integrated rate law of ln of A is equal to negative kT plus ln of A initial. I did it. And then a second order. All right, I'm blowing up my screen. Okay. Okay, so second order integrated rate law is going to be 1 over A at time t is equal to positive kT plus 1 over A initial. And I could show you the calculus behind how to do, like where these formulas are derived from. So you could actually do a third order, fourth order, fifth order, but you don't need to know those, so I'm not going to bother. And honestly, I mean, the calculus isn't too hard, but it's not worth going over right for a chemistry class. But in this case, since it's second order in A, that means it must follow this particular integrated rate law. There you go. I'm not doing a very good job of highlighting this. Okay. Okay. There you go. It's kind of coming together. All right. So that's the reaction that you'd have to use. And notice it's kind of like a linear reaction in the sense that you got the y is equal to mx plus b. K is the slope, x is the time, and 1 over the initial concentration is your y-intercept. So if you wanted to get a straight line here, the only one that would give you a straight line for a second order rate data would be C. C. So if it was a first order reaction, the only way you'd get a straight line is to graph ln of A over time versus time. If it was a zero order reaction, the only way you'd get a straight line is to graph A versus time. So, yeah. Oh yeah, no problem. Does that make sense? Any questions over this, or do you feel like this makes sense now? Awesome. Yeah, just a side note, if, for example, if I graphed the data for a second order reaction, if I graphed the data for a second order reaction, but I graphed ln of A versus time, it would look more like this. Or it would look more like this for the A, like that. So it would be curved. It would be curved. It'd be all weird. So it wouldn't be a straight line. If there was a second order reaction and I graphed those other two, you wouldn't get a straight line. Okay. So let's take a look at number 11. And number 11 is interesting because number 11 actually is similar in some senses to some questions you can get for nuclear chemistry, because the first order rate mechanism is actually all nuclear decay is a first order rate process. So the first order rate equations that you use for this for chapter, I think it was 14, are actually the same first order rate equations you end up using for nuclear chemistry. That says the half-life of this first order reaction is 13 minutes. The initial concentration is 0.085 molar. It takes how many minutes to decrease to 0.055 molar? So for something like this, since it tells you explicitly that this is a first order, and actually I'm going to go ahead and do this. Here we go. There we go. I want to draw. Draw, darn you, draw. Okay. So it's a first order reaction. Sorry, that's what I wanted to highlight. First order. I could care less about 13 minutes. No. But I do care about it, just not as much. So first order reaction, which means I'm going to use the first order integrated rate law, which is the ln of the concentration at time t is equal to negative kT plus the ln of the concentration initial. Now in this case, I'm trying to solve for the time. So if I rearrange this equation, if I subtract the natural log of the initial concentration minus the natural log of the initial concentration is equal to negative kT. I can then solve for time just dividing by negative k. A little lesson in algebra here. And that gives me t. Now another interesting thing about logarithms is if you have a log with the same base and you subtract another log with the same base, you can actually combine that into one log, because by subtracting you end up dividing the internal parts. What I mean by that is this. ln of a minus ln of b is equal to the ln of a over b. Or in this case, the ln of a at time t minus the ln of a initial is the ln of a at time t divided by a at time initial. Over negative k. And that gives you t. Now here's the thing. While we do have, and actually I'm going to move the t over to this side, t equals, that is a horrible t. Let's try that again. T equals, and then I'll erase this. Now while I do have the initial and final concentrations, final concentration 0.055, and I do have the initial concentration 0.085. I don't actually have k. So that means I have to solve for it. And if I'm solving for k, I have to actually first solve for the half-life. So since the half-life is 13 minutes, and if you're given a list of the equations, you may be given an equation for half-life. The half-life for a first-order process is equal to the ln of 2 over k. Sometimes they'll just put the value of the ln of 2. ln of 2 is approximately 0.693. But I usually like to just use ln of 2 because it's more precise. Okay, so ln of 2 over k, or 0.693 over k. Basically, I have to rearrange this to solve for k before I can solve the problem below. Multiply both sides by k, divide both sides by t1/2, and I get k is equal to the ln of 2 over t1/2. And so that'll be ln of 2 over 13 minutes. And if I do that, if I calculate that, I actually have to calculate that. It'll be 0.0533. And this will be minutes to the -1. So then if I plug that in here, whoop, plug that in down there, 0.0533 minutes to the -1. And notice that this is negative k, so I do actually have to put a negative down there. So then I'm just going to go ahead and take the ln of 0.055 over 0.085 and then divide it by that negative k, and what do I get? Yeah, 8.2 minutes. And then I'll put 8.2 minutes. So this is your answer A. Now, some problems like this, you can actually look at the answers and kind of deduce what it should be. For example, in this case, I can see that it's going from 0.085 to 0.055. Well, that's not half. That's not half, but it's not too far from half. It's about 1/3 of the way down. So because it's about 1/3 of the way down, you can imagine it's probably a little bit more than half of what the half-life is. But it's certainly not likely to be 3.6 minutes or 0.048 minutes. It's just not enough time. The truth is you really couldn't distinguish between A and E. And you really couldn't even say necessarily B without calculating this. Some of them will be obvious, like if it's at 15 minutes or 20 minutes, you could toss that out because for it to be 20 minutes, it would have to be less than half. 0.085 would have to get to less than half. It would have to be like 0.4 or 0.3 to get to for it to be 20 minutes, and probably even lower than that. But so in this case, unfortunately, you do actually just have to calculate it. Any questions on that? I apologize if I'm going a little bit too slow, or if I'm. Does anybody want to skip ahead to any particular question or topic? We only have about a little bit more than a half hour left, so I don't know if there's something that you want to cover that I might not get to if I just go in sequence. Okay, no problem. All right, so look at next stuff. It talks about equilibrium instead of rate. So that's it with rate. So equilibrium. The reaction below has a K of 997 at 472 at equilibrium blank. So what does the reaction of what does the equilibrium constant of 997 tell you? So if you understand that equilibrium is effectively the concentration of products raised to the power of their stoichiometric coefficient, of course, but generally speaking, it's the concentration of products times one another divided by the concentration of reactants times one another. When the top is greater than 1, or rather when K is greater than 1, it means that, yeah, exactly, 997 means much more products than reactants. If we, for example, if we put this as a something to 1 ratio, it's basically a 997 to 1 ratio. So basically, if K is greater than 1, that means there's more products. If K is less than 1, that means there's more reactants. So greater than 1, more products, less than 1, more reactants. If it's to be greater than 1, the numerator has to be greater than the denominator. To be less than 1, the numerator has to be less than the denominator. So yeah, definitely. That's a pretty straightforward question. Now if we look at this one, it says the equilibrium constant for this reaction, reaction 1, is K. What is the equilibrium constant for reaction 2? So we have to understand how manipulating this, so let's say equilibrium reaction for this is K. All right. Now, so this is equilibrium constant. K2 is K. Now, what has been done to reaction 1 to turn it into reaction 2? What has been done to reaction 1 to turn it into reaction 2? Yeah, it's been flipped and it's been multiplied by 3. Well, if you flip a reaction, since if we go back, if we look at back up here, K is products over reactants. By flipping a reaction, I flip the products and reactants. So that's going to actually make the new equilibrium constant for the second equation to be flipped. That means that this is going to be the inverse of the original. But not just that, you multiply it by 3, right? If I was to write the equilibrium constant for this in terms of the actual substances, I would say, well, it's the concentration of NH3 raised to the 2/3 power over the concentration of N2 to the 1/3 power times the concentration of H2 to the first power. And then if I would write the constant, if I was to write the equilibrium constant for the second one, it would be the concentration of H2, or concentration of N2 rather, to the first power times the concentration of H2 to the 3rd power, all over the concentration of NH3 squared. So remember that your coefficients here, these become your powers. Well, actually, that power. Okay. Kind of, there you go. The coefficients become your powers. So multiplying it by 3 actually raises the power. It raises the power. It multiplies the power by 3. So that means this is going to get raised to the 3rd power because I multiplied it by 3. I also see that the products and reactants have flipped. Products and reactants have flipped to get to the bottom, to get from the top equation to the bottom one. So it's been flipped and it's been raised to the 3rd power. And if I do just some basic distribution there. 1 to the third power is 1. K to the third power is k to the third. So the equilibrium constant for equation 2 would then have to be 1 over k to the third. Does that make sense? Students oftentimes get tripped up on that. That's the question that I get a lot of mistakes on. Okay. Let's hit the next one. So consider the following reaction. The value of Kc for this reaction is 1.10 at 25 degrees Celsius. What is the value of Kp for this reaction? So this involves knowing the Kp to Kc conversion equation. And basically, Kp is equal to Kc times RT to the delta N. Now, delta N is the change in the number of moles of gaseous products. Notice it's only gaseous products. I don't care about anything else. So, delta N in this case is what? How many moles of gaseous products do I have? I have 3 moles of gaseous products. How many moles of gaseous reactants do I have? No. Gaseous reactants. There you go. Yeah. Just the gases, right? So 3 minus 1. So gaseous products minus gaseous reactants. 3 moles of gas minus 2 moles of gas, or 1 mole of gas is going to give us 2. So this is our delta T, or delta N. Notice that if the number of moles of gaseous products and the number of moles of gaseous reactants are the same, like if I start with 2 moles and I end with 2 moles, then Kp and Kc are the exact same number, because delta N would be 0, and anything to the 0 power is 1. Kp and Kc are the same if the moles of gas on the product side is the same as the moles of gas on the reactant side. In this case, they're not, so I do actually have to perform this calculation. So I will simply go ahead and plug in the Kc value. Kp is equal to Kc, 1.10 times R. And I'm actually going to have to use this value of R, not the 8.314 joules per mole Kelvin. I have to use liter ATM because Kp is always given in terms of ATM. Kp is always given in terms of ATM. So this is going to be ATM. So 0.0821 liter ATM per Kelvin mole. And then that's of course actually this whole thing is going to actually RT. The temperature is 25 degrees Celsius, but of course I have to use Kelvin, right? Whenever you are using temperature in chemistry, you must use Kelvin all the time. Never, 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 never use Celsius. Unless it's a change in Celsius. Change in Celsius and change in Kelvin are the same, so it doesn't matter if it's a change. But if it's not a change, anytime you see T and not delta T, you must use Kelvin. Must use Kelvin. So anything thermodynamic related, Kelvin. Anything equilibrium related, Kelvin. Anything gas laws related, Kelvin. The only time you use degrees Celsius is if it's a change in temperature, like the freezing point depression, change in T. Okay, so then I just go ahead and crunch out that calculation, and if I do, I'm going to get something which I don't know because I haven't actually calculated it yet. And yeah, you get about 658. So the answer is A. All right. Any questions on that? Are we good? Let's Pretty straightforward one. Okay, cool. So, number 15 says at a certain temperature, a flask at equilibrium contains those concentrations. What is the value of Kc for the following equation? So this fortunately is a pretty easy one. This is just asking you to basically write an equilibrium expression and plug in the values to solve for Kc. So equilibrium expression, Cl2 times H2 over concentration of HCl. Concentration of HCl squared. Because don't forget you have to raise these to their stoichiometric power. The power of Cl and the power of H are just 1, so I don't need those. So then I just plug in the numbers and calculate, and I get some answer. That's good enough. I don't think we have to bother actually calculating that. I'll let you do that on your own. That makes sense? You all good? I know I kind of rushed it. Shame on me. I may be making a mistake trying to rush. I want to try to get through as much as I can for you guys. Okay. Number 16, the expression of Kc for the reaction below is what? What do you think? Yeah, A. Why do you not include the solids? Why do you not include the solids? Their concentrations do not change. Or more precisely, I guess you could say their activity is always considered to be 1. And that's the definition you'll learn when you get into quantitative chemistry. But essentially, yeah, the concentrations of solids do not really change, and therefore, as a result, they're considered to have a relatively constant activity, and so you can pretty much ignore them. So solids and liquids, you don't want to include in equilibrium constants. So yeah, A is the answer. Ignore me! Okay. 17th definition, Bronsted-Lowry base is defined as what? You know your definitions, don't you? What's a Bronsted-Lowry base? No? A Bronsted-Lowry base does not donate protons. Yeah, Bronsted-Lowry base accepts protons. The proton acceptor. A proton acceptor. So in this case, D. Proton donor is a Bronsted-Lowry acid. Proton acceptor, Bronsted-Lowry base. So Bronsted-Lowry acids and bases can really only be defined in the context of a chemical reaction, because there are some substances that will act as acids in some cases or bases in others. So there's not really a standard acid or base. For in the Bronsted-Lowry system, there are just things that are more basic and more acidic, and there's a lot of things that can act as both. All right. Whereas just out of curiosity, what do A and what do A and C represent? Definition-wise, what acid or base definition are represented by A and C? Just in case you get a question about something other than a Bronsted-Lowry base. Arrhenius, yeah. So A is an Arrhenius acid, C is Arrhenius base. Did you all talk about Lewis acids and Lewis bases? That is a subject that's going to be of great importance later on in organic chemistry. Usually they mention it, but just enough to give a definition. They don't really go into it too much. I'll just tell you the definition just in case you need to know it. A Lewis acid is an electron pair acceptor. It's an electron pair acceptor. So you can think of an example of a Lewis acid would be something like Fe3 plus is a really good Lewis acid. You have Fe3 plus ions in solution that'll actually jack up the, or hit down the pH, drop it down to about, 4 or something, maybe even lower. There are some Lewis acids and Lewis bases, or some Lewis acids that'll do even worse. Some of them will really drop it down. They're almost as strong as some of the strongest weak acids. But yeah, that's a Lewis acid. It's an electron pair acceptor. A Lewis base is an electron pair donor. And once again, these definitions are in the context of a chemical reaction. We oftentimes explain organic chemistry reactions in terms of Lewis acids and Lewis bases, electron donors and electron acceptors. So I'm not going to do 18 because it's too simple. All you have to do is take the negative log of that. That's not bother. In case you don't remember the formula, which you should, negative log of the concentration of H plus. All you have to do is take the negative log of that. You got your answer. That's pretty simple. So let's go to the next one. It says H plus concentration in a solution with a pH of 4.39 is blank. This just involves a little logarithmic mathematics. Once again, I'm probably not going to take too much time going through this, but essentially, if you do the logarithmic mathematics, 10 to the negative pH is equal to the concentration of H plus. If you need more explanation on that, please feel free to check out the answer key or to stop by the Science Learning Center. Cool. What is the conjugate base of NH3? The conjugate base for NH3? No. Conjugate base assumes that the substance indicated is an acid. Professors like to throw up tricky questions like this. Conjugate base of NH3 means that NH3 is acting as an acid. So if NH3 acts as an acid, we'll take water as our reference substance, even though this wouldn't happen in water, it would typically happen in something else. But if NH3 acts as an acid, that means it donates a hydrogen. And if it donates a hydrogen, what's left is going to be NH2 minus. So the conjugate base always means that the substance you're referring to must be the acid. So to figure out the conjugate base, you have to take an H away from it. Yeah, D. Some students would be tricked by this and they'd say it doesn't have a conjugate base, but it actually does. There are some really important chemical reactions that require you to use NaNH2, sodium amide. NH2 is called the amide ion, and it's a really, really good base. Very useful for certain reactions. Oh, good, yeah. Another question, like a question that professors oftentimes like to ask is they'll say, what is the conjugate base of HSO4 minus? And since HSO4 minus can either gain or lose one, the conjugate base of this would be SO4 2 minus, because conjugate base means this is acting as an acid. If it's at the conjugate acid of HSO4 minus, that means it's acting as a base, in which case the conjugate acid would be H2SO4. So yeah, watch out for those. Those are a little tricky. You have to really think about them. Number 21. This is the standard weak acid equilibrium equation. pH of a 0.15 molar solution of this is what? The Ka value is 1.8 times 10 to the negative fifth. So anytime you see Ka, and Kb are always weak acid or weak base reactions with water. It's Ka, so it's a weak acid reaction with water. So if HOAC reacts with water, this is a weak acid, so it's going to be in equilibrium, hence the equilibrium constant. What are the products going to be? Yeah, that's not terribly specific though. Hydronium ion in the conjugate base. So it will be hydronium. What is the conjugate base? Yeah, if the HOAC is acting as an acid, it donates a hydrogen to water, forming hydronium. The conjugate base will then be OAC rather, minus. I almost said AOC. I'm thinking politics or something. But yeah, so there we go. So now once you have the equation, you can write out an ice chart. Because it's asking for the pH. This is what it wants. And the pH is equal to the negative log of the concentration of H plus, or H3O plus. More accurately, the pH is generally speaking the negative log of the concentration of H3O plus. Okay? So in this particular case, I need to figure out what the H3O plus concentration is at equilibrium before I can find the pH. When you're given an initial amount and you're trying to find an equilibrium amount, an ice chart is always a good idea. So the initial amount of HOAC is 0.15. The initial amounts here and here are 0 and 1 times 10 to the negative 7. Because in a neutral solution, 1 times 10 to the negative 7 is the concentration of H3O plus. However, 1 times 10 to the negative 7 is really tiny. So unless you're dealing with really small concentrations, with like the 0.15, let's say it was 0.00000015, unless you're dealing with something really tiny like that, you're going to just go ahead and assume that the H3O plus concentration is actually 0. Okay, so now I don't know what the change is, but I know this has to be a minus x because I can't subtract from the products. Why can't I subtract from the products? Why can't I put the minus x on the product side? Well, it is true that the concentration of products increase, but how do you know that? Why is it impossible that the concentration of the products to decrease? Why would it be impossible for the concentration of the products here to decrease? Because it started at 0. Exactly. So you can't have less than 0, right? I can't have negative 5 people in a room. I can have 5 negative people in a room, but I can't have negative 5 people in a room. So this is going to be plus x. It must be plus x. So, yeah. Oh my goodness. Okay. So this would be 0.15 minus x. We always have to confront our calculations with reality. Okay. So this will be plus x plus x. Now, in other circumstances, if you already had some products to begin with, and you're trying to figure out what the change is, it is possible you can have a situation where the products decrease and the reactants increase, but it would have to be a situation in which there were actually some products already. But in this case, yeah, it's pretty obvious. Positive products. Okay, so the equilibrium constant for this reaction is concentration of H3O plus times the concentration of OAC minus over the concentration of HOAC. Then if I plug in my numbers, it's 1.8 times 10 to the negative fifth is equal to x times x, which is x squared, over 0.15 minus x. However, whenever k is times 10 to the negative fifth or more, or less rather, so 10 to the negative fifth, 10 to the negative sixth, whatever, the amount of ionization in that is so small that this minus x can typically be ignored. So let me repeat that. If this is 10 to the negative fifth or less, you can ignore that minus x. 10 to the negative fourth, sometimes you can ignore it, sometimes you can't. You gotta check it. Anything 10 to the negative third or greater, you're probably gonna have to use the quadratic equation. Because if I can't ignore that x, I have to use the quadratic equation, but chances are your professor is not going to give you a question on the final exam that requires you to use the quadratic equation. So in all likelihood, yeah, that's going bye-bye. So multiply both sides by 0.15 and take the square root of that. And that's going to give you 0.0 something or other. So 1.8 times 10 to the negative fifth times 0.15 square root. It's going to give you 0.00164 molarity. I can then plug that back up into my pH equation and take the negative log of that. And that's going to give me about 2.78. Okay, cool. So it looks like we're almost out of time, but I think we could definitely do 22, maybe even 23. So it says, which is the strongest acid? I'll help you out a little bit with this. To a strongest acid, you want the ion to which it is bound to be more. Okay, so I don't want to go through the whole REO, atom induction, or atom resonance induction, and dipole induction basically, and orbital. It's a little bit more complex when you get into organic chemistry, but simply speaking, you should have the 7 strong acids memorized. If I look at these, the only strong acids that I have are the last 3. So these are the only strong acids I have. Here's my strong acids. HF is a weak acid, HClO is a weak acid, and that you should just know from memory. However, between these 3 strong acids, there is one that is more strong than the others. Turns out there's 2 factors that determine the strength of an acid. One is electronegativity, and the other is polarizability. The more electronegative the atom bonded to the hydrogen is, the stronger the acid, and the more polarizable it is, the stronger the acid. Well, what makes it polarizable? If you go back to your intermolecular forces chapter, you should remember that the larger something is, in other words, the heavier it is, and the longer it is, the more polarizable it is. So if you have carbon atoms of the same, carbon chains of the same length, the one that's less branched is going to be more polarizable. The one that's more branched is going to be less polarizable. But in the context here, it's the size of the atom. The bigger the atom, the bigger the size, the more polarizable it is. So, and which one is a bigger factor? Which one's more important? Interestingly enough, it's polarizability. So polarizability is more important than electronegativity. So if I look at HF, HBr, HI, and HCl, Yes, fluorine is the most electronegative atom on the periodic table. However, of those four, which is the most polarizable? Hint, which is the largest ion? Which is going to be the largest ion attached to the hydrogen? Iodine, exactly. Iodine is the largest and therefore it is the most polarizable. So hydroiodic acid is actually the strongest of the strong acids. It is the strongest of the strong acids. One can make a case for HClO4. That actually could possibly be stronger. But of these, HI is definitely the strongest. All right, so then let's look at one last question and then we'll call it a day. In which of the following aqueous solutions would you expect AgBr to have the highest solubility? So in this case, we need to recognize that the common ion effect of Le Chatelier's principle, this AgBr is a sparsely soluble salt, which means it's only partially soluble. It's only very little of it is actually going to break apart. So the solubility equilibria here is solid AgBr is going to split into Ag plus and Br minus. Ag plus and Br minus. These are aqueous. Okay, so in which of the following solutions would you expect AgBr to have the highest solubility? Well, if I look at the first one, if I add LiBr, what am I adding? Am I adding products or reactants? If I add LiBr. Products. If I add products, what way is that going to cause the equilibrium to shift? Yeah, it's going to shift to the left towards reactants. So a shift to the left, is that more soluble or less soluble? Less soluble because it's forced into being a solid. So we see then that anything that's going to add an ion to the right-hand side of this equation is going to push the reaction to the left, making it less soluble. So will AgNO3 make this more or less soluble? Less soluble. Will NABR make this more or less soluble? Will KBr make it more or less soluble? So each of these things makes it less soluble than pure water. The answer, therefore, would be pure water. Now, if you were to have something like, have something like this, let's say it was silver carbonate. Well, 2Ag plus and CO3 2 minus. So you could get a question like this. Well, what about if I added HCl? What would that do? If I added HCl to silver carbonate, what would that do? What would the HCl do? It's not part of the equilibrium, but what could it do? Exactly, it would consume carbonate, so it would remove the CO3. And if I add HCl and remove CO3, what would happen? If I remove CO3, what would happen to the equilibrium? Which way would it shift? To the right, exactly. So if you have a situation where one of these solubility product constants has a substance that can be reacted with on the product side, if you react it and basically pull that ion out of equilibrium, that can cause the solubility to increase. But in the problem 23's case, each of those would just provide a common ion on the product side. That would cause the solubility to decrease. Does that make sense? Cool. Well, I regret that we're out of time. We only got, let's see, how much more problems did we have left? Yikes. Okay, so we got about less than halfway through. But the good news is that the complete answer key for this whole thing is up on our website. So the complete answer key for this whole thing is up on our website. Well, thank you. No, thank you very much. And so you check out the full answer key for any of the problems that we didn't get to that you want to kind of review. Furthermore, you can always stop by the Science Learning Center, the SE Science Learning Center, and we can definitely help you with any questions that you have. We're there 8 in the morning to 8 at night, Monday through Friday, and on Saturdays 10 to 4. I don't know when your final exam is, but please feel free to stop by and get help if you have any questions. Once again, thank you so much for coming. Feel free to check out our other resources up at our website. In fact, before I go, I think I would like to share that with you really quickly. I'm going to share my screen with you. Bam. So if you Google TCCSE Science, you Google TCCSE Science and you click on Chemistry Web Resources, click on the Google site page that we have. In fact, let's see if I just Google TCCSE Science Learning Center, come to our website, Chemistry Web Resources, scroll down to Chemistry 1412. There are video tutorials over every single topic for the entire semester. This is a video chemistry textbook, basically. Every single topic. Nuclear chemistry, you got questions, we got answers. Videos over every single topic. Half-life, fusion, fission, radioactive decay, all that good stuff. Furthermore, we also have practice tests with answer keys over every topic, including the answer key to this final exam, which I also sent out to you. Let's say you're taking Dr. Mohammed Chabouni. He also is teaching Gen Chem 2 this semester. You can look over his practice test and the comprehensive answer keys that show all of the work, and some additional practice tests as well that are pretty good. Let's see, what else? We also have chapter reviews. Sometimes when studying and doing practice problems, students tell me that these chapter reviews are really helpful for the final exam because they're basically a one-page summary of each of the chapters. For example, if we do free energy and thermodynamics, it will give you second law of thermodynamics, the definition, entropy, the definition of what entropy is, how to calculate entropy, products minus reactants. It gives you several different equations that you may have used in the chapter. It gives you an explanation of Gibbs free energy, explains it in a little bit more detail than even the textbook, makes it a little bit more understandable. How to interpret this equation. What does this mean when something is spontaneous at low temperatures versus high temperatures, and why? So, like I said, a one-page summary or a two-page summary that covers all of the topics that in that particular chapter. So these are really useful when studying and reviewing, going over some of the terminology and such. So please feel free to take advantage and use some of these resources as well if you think they could be helpful to you. All right, I'll get off my soapbox now, but it was fun having you guys here, and you all have a great day, and thank you so much for coming.